All right, so hello, good morning, everyone. Thanks for having me. Today I'll talk about Project Loom, which is an OpenJDK project aiming to bring lightweight concurrency mechanisms to the Java platform. And this short rationale sort of implies that our current concurrency mechanisms are not so lightweight. So I'm going to invite you to the journey I went through in order to understand what it means. And we're going to talk about synchronous calls, asynchronous, blocking, non-blocking, and reactive before introducing Loom properly. So in order to experiment, I needed a use case. So I took a piece of program from work and I've simplified it a bit. So here we have a service to which clients connect to in order to download something. All right, so let's say it's a file, for instance. But this resource is kind of precious, so we are going to act as a proxy. And we are going to first try to get a token from a coordinator in order to download our resource. We are going to we may have to try a couple of times before we are successful in getting a grant. And when it's finally okay, we are going to start to stream back the content to our client. And in the meantime, periodically send earthbit requests to the coordinator so he doesn't revoke our token. All right, so keep in mind this is just a simple demo use case to experiment with things, and it is absolutely not a benchmark. All right, so I'm just going to simulate 200 clients and see how it goes. So the first implementation I've made of this small service was the most simplest one I could come up with. So maybe people in the room are going to die just by looking at this thread.sleep method. But keep in mind, this is really simple, easy to read, easy to understand, easy to write code that any junior Java developer can understand. So this is nice synchronous code that we're used to. So let's see how it goes on the efficiency side. On the CPU utilization is really low, actually, and it kind of makes sense, right? Because we're not doing anything. We're just sending a bunch of requests, waiting for a result. We're not computing any math, any sorting algorithm, or something like that. We're just sending requests and waiting for responses. What's more interesting is the number of threads we are going to create, right? So for 200 clients connecting simultaneously to my service, I'm going to first start the first bunch of 200 threads to handle them. And then it's an implementation detail, but 200 more threads to handle periodical earthbit requests. So let's see why we are creating so many threads and what are they doing, right? So if you look at our threads, they are waiting a bit at the beginning. So this is because of the retrying loop in order to get a token. And then when the download starts, they all seem kind of busy, which is a little bit weird, right? Because, as I said, we're not computing anything at this point. We're just sending a bunch of requests and waiting for response. So let's see what those threads are usually doing. We can see with the thread dumps that our threads are running actually this socket dispatcher.readZero method, right, which is a native method. And they are actually not running it, they are actually spending most of their time in it, right? And this is where lies the problem, right? Because this read method on a blocking socket is going to is actually a blocking call, right? So let's see what's a blocking call. For the sake of this first implementation, I've used a socket channel, which is by default a blocking socket channel. So again, for the sake of simplicity, let's just assume that we have two types of code that we are running on our CPUs. All right, we have user code, and we have the kernel code, which is handling the low details. Here, I have this run task, which is running, and it's a code which is implemented inside of a runnable, which I have submitted to, in this case, a cached thread pool executor service, which is going to match a runnable task with a thread inside its unbounded pool. And when it doesn't find a thread available, it's going to create a new one. All right, so this set of instruction, actually, when we look more into the details, it looks more like this. All right, this is what is called a context switch. And again, to make things simpler, here I have modeled it. I have a schema which represents it with just 2 steps, right? So the first step is to suspend the currently executing thread. All right, so we are going to, actually not us, the kernel scheduler is going to save the call stack of this thread. It's going to save its registers, put those things in a data structure, and put the thread back into the queue. and maybe reschedule it later when the result of the call is available, all right? And the second step will be to actually schedule the next thread, the next runnable in the next thread in the queue, in the priority queue. And when these tasks run, it may or may not have blocking calls too, but at some point later in time, the result of the blocking call of my round task is going to be available, and then the scheduler will restart this other thread. And this is actually really bad, because assuming I can have thousands or even tens of thousands or millions of TCP connections opened on a single box, it means I'm going to create as many threads per client connecting to this box. So it means I'm not going to waste tons of memory usage to just save the states of threads that are just really not doing anything. I'm also going to waste tons of CPU cycles to do context switching and bookkeeping, and those cycles will not be used to run my useful application code. Sorry. But so, hey, they say that asynchronous call is more efficient. So maybe let's try to write a second example where I'm going to go the async road. So in this second implementation, I've used, instead of a cached thread pool executor service, I've used a scheduled thread pool executor service, which is bound to a certain number of threads. And schematically again, all the threads in this thread pool are going to run some kind of while loop forever, and waiting for tasks to come down the executor's queue and execute the runnables, all right? The first thing with this implementation is it quickly gets kind of messy, right? Because it's easily, I mean, it's doable when we have one or two asynchronous calls and you have to split your logic, but I mean, you can handle it. When we have 3, 4, 5 or more asynchronous calls and you have to keep references to asynchronous tasks to handle dependencies and etc., it quickly is hard to enter, and it's actually known as the callback hell. It's the name, so it's a known problem. But hey, I mean, if it's the way to more efficient code, okay, why not? So in this example, I've used 3 executor services just to make things clear what everything is doing. One is to handle client requests, one is to handle requests to my remote services, and one is to handle the earthbeat request. All right. So again, what I see here is that those 2 thread pools I've created, the pulse one for the earthbeat requests and the third one for the requests, they again are not doing many things, because actually they are just handling events, right? They are taking runnables and making asynchronous calls to the next function. So they are just sitting there waiting for more tasks to come down to the executor's queue, actually. So they don't have many things to do. But my service requests here, again, they still look kind of busy, right? So I think maybe you can see where I'm going. But those threads, because I haven't changed the implementation of my client on purpose, they are still doing this read blocking system call. All right? So this is just a quick reminder that async doesn't mean non-thread blocking. All right? They are not synonyms. And actually, we see later that asynchronous, synchronous, or thread blocking and non-thread blocking is quite orthogonal. But if you put thread blocking calls into runables that you submit to, for instance, a scheduled executor thread pool, all you'll be gaining is latency, basically, because your threads are going to be blocked. Because they are bounded, the more runnable you submit to the scheduler, they are going to be just piled up into the executor's queue, and yeah, you're just basically gaining latency, that's it. And yeah, it's also a reminder that asynchronous is quite hard. I mean, I've made a mistake when implementing this first version, and I ended up with creating 800 threads for 200 clients, which is really, really bad. So if you want to do non-blocking on the JVM today on the Java platform, you have to use some other packages, such as java.nio package. And here I have made a third implementation of my client using an asynchronous socket channel, which use, as said, a non-blocking socket channel. So I'm connecting to my server, I'm writing my headers and etc. to start the request, and I'm reading the content to get the response. All right, so here we're still asynchronous, so we still have to split our logic into tasks and callbacks and etc. But we are handling an API that is really low level. So, but here again, if it works. I mean, right? You can handle tons of requests on a few number of threads. You have effectively multiplexed the number of clients requests you can handle on a small number of threads, because all those threads are doing is, again, handling events. They are sending a request to the executor, which is so a runnable containing non-blocking calls, to which you register callbacks. And when the result is available, the callback will be called. And because I'm not doing complicated logic, my threads are just there sitting, waiting for more tasks, so I could be handling way more clients than my 200 simulations. And I could actually have used just a single thread to do all that. So here you can see that my threads, again, they are just handling events and not doing many things. But you can see this huge tower of asynchronous call, which are from my dummy client, because I've made quite a simple implementation of my HTTP client. And because this is a so low-level API, it's hard to maintain, right? And if you want to be, again, more efficient, you may decide to use system calls like EPOL or KQ, etc., how they're named on their other OSs, and an event loop pattern, right, to register monitors on file descriptors and just handling reading and writing from and to buffers when there is data available or when you can write from them. And this is actually what Netty is doing. So it's not a surprise that Netty is kind of the building block of a lot of microservices today. It's because it's in a library which is really well implemented and efficient, but it's still asynchronous. Okay, you still have to manage callbacks, split logic, and personally, I just don't like it. Not Netty, right? Splitting my logic. But for a couple of years now, we've had this reactive stream implementation, and we have binding for them, so it brings us a really nice declarative functional API on top of all this asynchronous mess. And for the sake of this example, my fourth implementation was with reactive using the reactor implementation from Pivotal of reactive streams, and the Netty binding, which is surprisingly named reactor Netty. So here on the efficiency side, we can see we have those thread event loops that are running, and they are actually doing work, right? They are monitoring file descriptors to see if you can read and write from and to buffers. And my parallel threads, they are, again, not doing many things, they're just handling events, so I could handle tons of clients this way. But on the user side of things, I mean, reactive works well when you have simple chaining of operators and logics that follow this way. But when you have to do something more complicated, or let's say that they are not already present in the reactive operators you have in your library, you might have to do quite complicated things. For instance, this is my simple retry loop, right, that we saw at the beginning. The synchronous version was really easy to understand, and here I have my implementation, which is buried under a ton of accidental complexity. This is not business code, right? This is just complexity brought by the library. So the question is, can we benefit from those asynchronous non-blocking calls, but without having to split our logic and do asynchronous? And can we benefit for all these libraries and event loop patterns without having to change paradigm and go the reactive streams way? And this is actually the problem that Loom tries to solve by bringing user threads to the JVM, aka fibers. So lightweight threads, or user threads, green threads, fibers, coroutines, etc. Conceptually, they are all the same thing. All right, they are different implementation of the same concept, which are user threads. And user threads, you can think about them as usual threads. You have sequence of instructions that are going to be run. They have the proper call stack, but they are not managed by the kernel scheduler. They are going to be managed in user space by a user space scheduler, right? So there will be more lightweight, less memory allocation, and they will not suffer from heavyweight context switches on the OS side, and we will just be handling tasks, but we'll see later how it's done. So fibers or user threads, in Project Loom, they have decided to implement them on top of continuations. So quick survey, who in this room has already heard about continuations? All right, so not too many people. Continuations are not new. They are from the 50s or 60s. They are really famous in programming language academic domains. So in the literature, a continuation is referred to as the rest of the execution of a program or of a routine. So you can imagine that you have a function, for instance, and at any point inside the instructions of this function, you are going to be able to insert a special statement, which is going to act as a point of suspension, right? So when your function is executing, it will actually stop on this special instruction, and it will return the control back to the code the caller who made the code. But you will have the ability in other branches of your code, maybe in another task run by your scheduler, for instance, to refer to this function and traverse a portal to go back in time or in space and continue the rest of the execution of your function. So it may kind of be alien at the moment, I've lost a slide. All right, not worry. It may seem weird, okay, when I talk about continuation like that, but actually you're doing it on a daily basis when you do asynchronous calls. You have your tasks, you have your instructions, and at the end of it, for instance, you're going to make an asynchronous call, and you are going to split your logic and effectively give back the rest of your logic to the asynchronous call in the form of a callback. All right? You're doing what is called as continuation passing style. Right? You're giving the rest of your execution to the asynchronous call. So let's try to be more concrete. Imagine you have a caller and a continuation and a runtime. All right? The caller is going to call a method run on this continuation. Imagine that this continuation is just a runnable for the moment. Inside this runnable, you will have the possibility to insert a yield statement, which is a special instruction that is going to give back the control to the caller, kind of like a return statement. All right? But instead of just throwing away the call stack of your continuation like you would do for a runnable, here the runtime is going to save the call stack of your continuation and put it somewhere. And when some later time another caller or the same caller wants to resume the execution, it's going to call the run method of the continuation again, and the runtime is going to restore the state of the continuation, its instruction pointer, and contrary to a runnable, which will start again from the beginning, this continuation will start from where it left. All right, and continue to execute its instruction just as long as it meets another yield statement or a return. So to explain continuation, this way is a bit complicated, but if we were to implement them ourselves, we might do it by using a pattern known as a finite state machine. So let's try to do it together, all right? We are going to have a caller and a finite state machine, and when we call run, and our finite state machine calls return, we are going to have to save the state somewhere. And for the sake of this example, I've used an iterator. So I'm going to assume everyone here knows what an iterator is. So to implement an iterator as a state machine, first I'm going to need a state. So here it'd be a simple integer. And this iterator, when the client calls has next, is going to be returning true just as long as we haven't reached our final state. All right? So on the first call to the next method of my iterator, my state will be 0, all right? So I'm going to go to this switch state statement, and in case 0, I'm going to first increment my state, and then I'm going to return, for instance, some value, an A. All right, so I am explicitly returning control back to the code that made the next call. And at some point in time later, if the client wants to call next again, I'm not going to start right from the beginning, right? Because my state has changed. I'm going to start from the case 1, again, increment my state, and return some value, giving back the control to my caller again. And etc., until I reach my final state, at which point my client is not supposed to call me anymore. With this example, which is pretty basic, I want to show you that you could implement continuation yourself in your code. Just imagine that in this case 0, I increment my state, and instead of returning A, I'm going to make an asynchronous call, an asynchronous non-blocking call, all right? And the callback I'm going to give to this asynchronous call is going to call this next method again. So when the result of my asynchronous call will be available, this callback will be called, and I'm going to go into the second state with the result of the asynchronous operation. And I'll be able to keep all my domain logic, my business logic, inside this function. All right? So it works, but it's not really fun to implement our method like this. So this is what Loom brings us. So it's a way to shift back from asynchronous to synchronous without having to write our code as state machines like that. So as I said, with support from the JDK, the implementation of continuations, and a scheduler, we have fibers. And we are going to pass our runnables into this fiber scheduler, and it's going to wrap our runnables into continuations. And when we are going to make asynchronous non-blocking calls, it's going to suspend the continuation, attach the run method as a callback to the continuation, and then schedule the next task. And when the result is available, the continuation will restart, and on the all the bookkeeping will have been done by this scheduler. So what's interesting is on the user side of the code, to implement my 5th version of this service based on fibers and continuations, I just had to copy and paste my first implementation, which was synchronous and blocking. All right, this is the exact same code. I have thread.sleep, which is actually non-blocking. And my request will actually be non-blocking. But I still have this nice synchronous API. All I had to do was to submit my runnable to this fiber scheduler, which is here hidden by this fiberscope.background call. On the efficiency side of things, I have 12 threads, 1 per core, which are managed by this fiber scheduler. And with them, I can handle all my requests. And again, my threads are just waiting for more tasks. I could be handling way more clients than this. All right, so here my threads are named for join, pool, etc., because the fiber scheduler is actually a modified version of the for join pool scheduler, which is a work stealing scheduler. And I have 3 more threads that are provided by the JDK. First, the fiber unparker is the one that is responsible for resuming the continuations when the result of the asynchronous call is available, and it's notified of the results of those asynchronous calls by those 2 threads, read polar and write polar, which are actually event loops, same as you've seen in the native reactive implementation, that are just attaching monitors to file descriptors and seeing if they can write or read from 2 sockets. So the current state of the Loom project is a prototype. Okay, so you can start to play with it, like I did by either building the JDK yourself or retrieving one of the already pre-built, I think it's JDK 14 early access on the Loom branch specifically. And you will be able to play with continuations, with fibers, and the provided scheduler, and you will be able to make non-blocking API calls with support from the the Java and IO methods that have been modified. If you want to do that, I highly encourage you to go to GitHub and look at a repository made by Remy Forax, which is called Loom Fibers, in which he has made tons of experiments with continuation. He has implemented lock mechanisms. He has re-implemented schedulers. So it's really interesting to see how it works. I mean, in the really low level. And if you, like me, if you really want to instead understand what Loom will bring to your day-to-day development, I highly encourage you to go see this library, which is named Quasar. And Quasar is actually an implementation of continuation and fibers available on the JVM since 2013. All right, so you had fibers and continuation on the JVM for more than 6 years now. And on top of continuations and fibers, they have implemented a lot of use cases. So the CSP model from Tony Howard, etc., will give you channel and transformations, and you have an actor model on top of it. So if you want to try it, I encourage you to give it a shot, and you'll see what you can do with fibers and how you have to eventually change your code to make it work with fibers when Loom will be available. And if you are on the Kotlin side of things, I encourage you to play with coroutines because they are actually the same thing. It's just that they are implemented inside the compiler instead of inside the JDK and etc. So it's just an implementation detail. Next on the Loom show, so as I say, Loom is the prototype, and continuations and fiber, they were actually the first steps of the project. And the next step will be implementation of tail call optimization, from which I can't talk about because I haven't started the work on this yet. But I can talk about this concept that is named structural concurrency, which I had quite a hard time to understand. So I thought it might be very interesting to you. Structured concurrency is something that is currently talked about in the mailing list and of the Loom project. And it's actually a way to draw a bounding context around your concurrent operations in order to avoid to have concurrent operation go rogue. So just because you like, I hope you like to have scope variables and you like if statements and while and try catch and etc. to give scope to your code. Structured concurrency is trying to do the same thing for concurrent operations. So you're going to draw a context around your concurrent operations, and you're going to be able to cancel all of them at once by just canceling this one scope. Or you're going to be able to say that, for instance, the whole scope should be cancelled if any one of those concurrent call fails. And you have a lot of reading on this, and this blog post seems to be the seminal work that introduced structured concurrency, so I highly encourage you to go check this out. All right, that's all I had. I'll be answering questions off stage if you want to. I have added a couple of references if you're into papers and readings and etc. And the repository for Loom fibers from Remy Forax, and my own repository if you want to see the experiments I've talked about earlier. Thank you, guys.